So thank you very much for the invitation. It's a pleasure to be here. I'm going to talk about a specific thing called model stealing, but before that I'll give a little bit of an overview of the context under which we are talking about things like model stealing. Whenever a professor comes and talks to you about some research that they are doing, all the hard work is done by the students and postdocs in the group. So I want to sort of recognize the set of people. Doesn't seem to. The set of people who contributed to this work. These slides are already on my website. You see the website address there, but if you also Google for my last name, you will find my website. So if you want to follow along, you can download that, or you can look at that later on. So like I said, I'm going to give a very quick overview of the big picture about AI, security, and privacy, why we should care. How do you go about systematically identifying what kind of security and privacy threats that one might run into. And then I'll dive specifically into model stealing. What is model stealing? Why is it a concern? And then we'll sort of look at specific things like, can models really be stolen? What can be done to counter model stealing? Are there defenses? And then if we have time, we have about 1 hour, right? Is that correct? Who should I be asking? We have about 1 hour, right? So if you have time, I'll sort of delve into a couple of more current research issues about whether model stealing, model ownership resolution schemes, which is one kind of a defense, whether they are robust, and also sort of practical concerns like what happens when you want to protect your machine learning model or AI model against multiple different threats. So let's dive into the big picture. So I don't think I need to convince this audience that AI will be, or even is, on its way to being pervasive, meaning that this is a chart that plots year on the x-axis and North American AI market size. I could have picked anything else. I could have picked the number of people who are doing research in AI, the number of startups that are working on AI. All of these graphs would look like this. It's exponential, right? But the extent of AI is not just in volume, but also in scope. Right? AI is affecting every aspect of our lives. People are using AI for precision medicine, personalized precision medicine, so the treatment for you will be based on data that's collected about you, and that'll be effective specifically for you. People are using AI in law enforcement, in jurisprudence, paroles granted to prisoners based on an AI model. People are using AI in human resources. I mean, if you're applying to a job, to any medium or big company, your resume is going to be read by an AI first, and only then a human would look at that, right? And cybersecurity is not an exception. In fact, my background is not AI. I was not trained as an AI person. I'm a system security person, and I started looking into AI as a tool. Can I use AI to solve cybersecurity and privacy problems? And down the line, we realized that the cybersecurity and privacy of AI itself is an open issue. But many cybersecurity people like me initially started using AI as a tool for intrusion detection, for detecting malware, for detecting Trojan horses, and so on. So you see that the scope of AI sort of reaches out and touches every aspect of human life, different kinds of professions, and your work and your hobby, and so on. So whenever technology is this successful, and for good reason, right? AI holds a lot of promise. We have already seen evidence why these promises are likely to bear. Whenever technology is this successful, it will also attract bad actors. Bad actors who would want to circumvent the technology or somehow make it less effective or use the technology towards their own ends. We have seen it happen with software, right? So 50 years ago, software was a niche thing. Once software started eating the world, bad actors figured out how to write malware, how to write ransomware, and so on. We have seen it happen with internet. Internet initially was designed with no security in mind, and once internet became such a runaway success, people start using internet for all kinds of things, like spam, like scams, and so on. So it's blindingly obvious to me that this is going to happen with AI as well, right? Any successful technology attracts bad actors, just as it attracts exponential rate of investment and so on. So how do we then go about identifying what these bad actors can do. So namely, what are the security and privacy concerns that these bad actors bring to bear, and what can we do about that? And if we don't address these security and privacy concerns, if people start to see that adversarial behavior by bad actors is going to sort of dent the benefits that AI brings, then the overall level of trust in AI as a technology is going to go down. That's the reason why we should pay attention to identifying what these concerns are and hopefully doing something about that. Right? So these are the challenges in making AI trustworthy. Now, these are the security and privacy concerns are challenges that arise because of an adversary, because of some sentient human being who's trying to sort of subvert the system, right? But those are not the only things that stand in the way of we as humanity developing trust in AI. There are other concerns that do not involve adversarial behavior, but nevertheless are equally important for developing trust. So you may have heard about things like fairness, like does a model make fair decisions? I told you earlier that models are being used for jurisprudence, giving out parole, law enforcement. And if a model is unfair, like if it treats one group of people differently from another group of people, that's a concern. There is no adversarial behavior here. There is no intelligent person who is trying to subvert the system. But if there is some kind of model, built-in biases in the model, that can also lower trust. So I'm not going to talk about those kinds of concerns which don't involve adversarial behavior, but I'm going to talk about primarily security and privacy concerns that arise because of an intelligent adversary. So to give you an idea of what kind of concerns we are talking about, let me give you an example. So for the rest of this talk, I'm going to use the words AI and machine learning as if they are synonyms. Machine learning is only one kind of artificial intelligence, but it's perhaps the most dominant one and the most successful one. So whenever I say AI, think machine learning, and whenever I say machine learning, think AI. So in the last 15 years or so, people have noticed that machine learning models can be evaded, meaning that they can be made to do the wrong thing by subtly manipulating the inputs that you give to them. Right? So here is an example. A kind of machine learning models that academics are fond of studying are called classifiers. Classifiers are given some input, the machine learning model figures out what class or what category it belongs to. So one type of classifier is an image recognition classifier. Given an image, it should tell you what type of object it is. Right? So if I show you this object and ask you what class is this, what is the category of object that's here, I'm sure you will come up with different answers. Anybody want to sort of hazard a guess? What is the class in this object? You can think about sort of coarse grain categories or fine grain categories. Anyone want to hazard a guess? Somebody might say a vehicle. Yes, it's a vehicle. You can maybe more narrow it down. You probably don't see this here. In North America, kids go to school in buses. These buses are always yellow buses. So anyone in North America who sees this will say that this is a school bus. Right? And classifiers 10 or 15 years ago were very good at classifying this as a school bus with very 99% accuracy and high confidence. It turned out that if you add a small perturbation to this image, so add a little bit of noise, and the resulting pictures looks like something like this. If I ask you the same question, you will say it is still a school bus, right? I mean, it clearly has all the features of a school bus. But the state-of-the-art machine learning models were completely confused, and not only so, that they did so with high confidence. So they would say this is an ostrich with very high confidence value, like 99% confidence or whatever. So this is discovered for neural networks about 10 years ago. But for other types of machine learning models, it was known even before. And if you think about it, when you have any kind of complex real-world phenomenon, and you try to represent that using a limited number of dimensions, such errors can occur, right? And you can, I'm sure you have come across similar evasive behavior against your own brain as the model, right? So you heard about, say, optical illusions. So optical illusions are inputs that are sort of cleverly crafted so that your brain is fooled into making the wrong conclusion, right? I'm sure you all sort of recall optical illusions that you have seen in books and magazines and so on, which, for example, there'll be like two lines of equal length, but you sort of put different kinds of twiggles at the end of the lines, and your eyes are deceived into thinking like one line is longer than the other. That's an example of an adversarial example. These are called adversarial examples. This adding perturbations to inputs is called an adversarial example. And so this is an adversarial example against a machine learning model that classifies images. Optical illusions are adversarial examples against your own brain. So the fact that adversarial examples exist is not a surprise. Even your own brain is subject to that. And I think any complex system being modeled with limited dimensions is going to be subject to that. What was surprising was how easily you could find adversarial examples against classifiers and so on. Were you asking a question? Oh, no, sorry. It also turns out, and we'll come to this later, that sometimes these adversarial examples are transferable, meaning that if you have a model and you find an input that will fool that model, and then if you have a different model for the same task that is trained independently, not all the time, but sometimes these adversarial examples against the first model will also be an adversarial example against the second model. Right? So that's called transferable. So keep that in mind, and we'll come to this later. So this is one example of a security privacy problem. And how do we go about systematically finding all the problems that might occur? And this is sort of what we teach students in system security, right? So we teach students to approach this problem systematically so that they can enumerate security privacy concerns that might arise in a system. So in a machine learning based system, you could start by saying, like, what is a machine learning based system? You could sort of, at some level of with some level of approximation, you could imagine that a machine learning based system looks something like this. At the far end, there are data owners who contribute data. So imagine you're all using smartphones, and when you type using the touch screen, you are providing sort of keystroke data, and your OS manufacturer, Android or Apple or whoever, is collecting this data. So you're the data owners who are contributing this data. They collect all this data into a data set, and then, like a human expert, using some framework like I don't know, like TensorFlow or PyTorch or something like that, and maybe using some third-party libraries, they would train a model using this data set, and that's the resulting machine learning model. Right? So in the case of handwrite keystroke data, the machine learning model would, for example, predict what is the sort of next word that you're going to type based on lots and lots of data collected from other people. So once a machine learning model is created like that, in order for it to be useful, you have to make it available to potential users or customers, right? And typically that's done via some kind of interface. Right? So there's a client who doesn't normally get access to the machine learning model directly, but they get to use the machine learning model via some interface. So think about, say, Google Translate. You have two kinds of interfaces. You have the web interface where you can type in some text and Google Translate will translate it for you. Or you can have a programmatic interface where your own application can use that API to talk to Google Translate as part of the application itself. And typically, this API also has some kind of access control so that only the authorized people, only the right people can use the model. So if this is sort of if you agree that with some level of approximation, machine learning systems look like this, you can systematically ask this question: who is the adversary? Who is this bad actor? And where is this bad actor located in this model? And what is the adversary's target? That'll give you one kind of risk. And you can systematically go through this and say, now, could this be a bad actor? Could that be a bad actor? And so on. And my thesis is that you will then enumerate all the security and privacy problems that would arise because of adversaries like this. Right? So in the next couple of slides, I'm going to use this notation. So I will indicate the bad actor in red with this kind of a sort of an icon. And the target of the adversary would be in blue. So the example that I showed you before, where the image classifier was fooled, was something where the bad actor is sort of on the far side of the interface. It's not necessarily the client that's interacting with the model. It could be somebody else. And what they control is the input. Right? So they perturb the input by adding some noise or something like that. and their target is the output. They want to fool the machine learning model into making the wrong decision. So you might think that if a school bus is misclassified as an ostrich, that's harmless. But you can easily imagine places where it would be harmless, right? So for example, if you have an autonomous driving system, that consists of an image recognition model that is sort of constantly taking pictures of what it sees, and it has to interpret what is in that picture, right? So if it has to interpret things like, is there a stop sign? And if there's a stop sign, it should tell the driving part of the model to slow down and stop. And people showed that if you could now sort of adversarially perturb this input by attaching little stickers and so on, for the human eye it looks the same, but a machine learning model used in an autonomous system might be completely fooled into misclassifying this as something else. And that obviously is a safety concern, right? So again, these were demonstrated in the last 10 years. So the threat here is an adversary is trying to compromise the integrity of the model by making it do something other than what it was intended. And the reason to do that would be to sort of evade the model, right? So imagine that this model is being used for some kind of access control, and your rationale for evading the model would be to break the access control, right? So imagine that this building has a camera in front, and it uses face recognition to let people in, and there's a bunch of authorized Rootcode employees who are allowed to come in. And if I know one of the employees, I can sort of change my face subtly so that it's not obvious to a guard standing in front of the door, but I can fool the camera system into misrecognizing my face as a Rootcode employee's face. So that would be a case of evading the model. People showed this in the case of classifiers, but these are not limited to classifiers. I mean, in these couple of slides, I'll show you examples of similar concerns that arise with generative models as well. So this is one example, right? So model integrity. We think about a second example, which is relevant to the rest of the talk. So here, again, the adversary is on the far end, and the adversary continues to control the input. But this time, the target of the adversary is not influencing the output, but the model itself, right? So by asking questions, perhaps in cleverly crafted ways, the adversary wants to use the responses, repeating the questions or asking multiple questions, getting the answers, and using that to build its own model, like some sort of a stolen model. And ideally, I guess the stolen model has similar functionality like the machine learning model that is the target. And if they can succeed in doing that, that'll be equivalent to stealing the model, right? So this is called model extraction or model stealing. So you can steal a model in different ways. You can steal the model, the bits and bytes of a model. That's called like white box stealing. We'll come to that in a minute. But here, what this picture shows is that it seems to be possible to steal a model without having direct access to the model, having access only via this API or this interface. So the color code here below is that papers that are in blue is work done by my students, and papers that are in black are work done by others. So we got interested in this about 5 or 6 years ago, where there were papers that showed simple models, logistic regression models could be stolen. We showed that like neural networks could be stolen, and then very quickly others showed all kinds of models could be stolen. And so again, that's not limited to classifiers. I'm sure you all heard this saga when DeepSeek announced a competitor to OpenAI's model around Christmas time. At some point, OpenAI sort of implied that DeepSeek may have stolen their model. DeepSeek may have built their model using OpenAI's model by paying a subscription to OpenAI and asking queries from OpenAI and getting the responses and using that to refine their model. So model stealing is not a sort of a entirely theoretical concern. If a major AI provider is accusing another major AI provider of stealing the functionality of their models. So I hope I sort of gave you an overall idea of what is machine learning security and privacy and why one should care about that. Now we'll sort of dig further into model stealing. But before that, let me pause and ask if you have any questions or comments on what I have said so far in this big picture. No? Feel free to interrupt me at any point, right? It's much more fun if you ask me questions as we go along, and we don't really need to get to the end of this presentation. I think we can stop whenever the time is up. But it's, I think, more valuable to you and also to me if you interrupt me and ask me questions. Okay, so is model steering an important concern? I sort of partially answered that. I showed you examples like OpenAI versus DeepSeek. But why is it a concern? So people, companies like Rootcode and like others invest a lot of effort and energy into building models because you realize that this could be a business advantage to you, right? It could sort of give you a leg up over your competition. That's why people are excited about building models. But this business advantage comes at a cost, right? So you have to gather relevant data, which is perhaps a big thing, but also like making sure that it's the right data. So in the case of classifiers, you have to label the data. You may have to curate the data. You may have to sort of clean the data. That's perhaps the most expensive process in training a machine learning model. And then you also have to have the expertise required to sort of choose what is the model architecture, how do you tune the parameters, and so on. And then the actual cost of training the model, the processors, the GPUs, and so on. All of this goes into giving you this business advantage, right? So if somebody could get the same business advantage without paying some or all of these costs, that's the incentive for them to steal, right? So if Google has spent a lot of money to build Google Translate, and if you could ask a bunch of questions from Google Translate and build your own translator, even if it's not as good as Google's translator, you might be incentivized to do that because you don't have to suffer the advertisements that Google would show you, or you don't have to pay subscription to Google, and so on. So notice that I put this word steal in quotes, and that's for a reason, right? So we'll come to see later that stealing might not be a bad thing, and you might not necessarily want to prevent stealing, but nevertheless, you may need to allow this in a sort of a control setting. So whenever I see stealing, I don't really want to give the impression that it's a bad thing and it should be stopped, but rather understand what it means and whether it undermines the interests of the entity that originally trains the model. And I think that should be our focus. So we'll return to this later. But for now, think about stealing as if you derive your model from my model without my consent, that's what we would refer to as stealing. Okay, so how to prevent model stealing? And so I already said that it may not be something that you want to prevent, but you can think about sort of if it's an outright theft, right? So if a model theft happens by the adversary getting the bits and bytes that constitute the model, then there are different ways that you can imagine to prevent this, right? So you can host the models behind a firewall. So this is what Google does. Google doesn't give you access to the model. It puts up an API. There are techniques to protect the models using hardware. So even if the model has to be sent to your device, if your device has hardware security mechanisms I can rely on the hardware security mechanisms on your device to prevent you from stealing the bits and bytes, but only sort of let you use the model via an API. There are also techniques that allow you to work with encrypted data, right? So I can encrypt the model and send it to you and make sure that you can only use it on your own model, on your own device, but you won't be able to take the model and ship it somewhere else and so on. So all of this essentially turn the white box theft of a model into a black box thing by sort of putting some kind of control around direct access to the model itself, right? But I already alluded to you when I showed you this initial slides that this is not enough to prevent model stealing, because you could steal a model by repeatedly asking questions from the target model and using the response to build your own model, right? So you're not stealing the bits and bytes of the model, but you're stealing the functionality in some way. So can models be stolen via these APIs? And so this is what work done in the last 10 years or so have shown that increasingly sophisticated model stealing is possible. People started with simple logistic regression models, then when showed that neural networks could be stolen via the API. Later on, people have shown that graph neural networks could be stolen. There's even a paper that showed that they were able to steal a version of Google Translate at the cost of something like $12,000, and it was sort of a real life example. I think I'll have a example of why they did that and and what they were able to do with this. This is essentially something that we already went through, right? So the reason why model stealing via an interface is possible is that every time you ask a question from a model, it serves as an oracle. It gives you a little bit of information, right? So intuitively, it's not surprising that if I could ask enough questions from a model, then I would have enough information to replicate the functionality of the model. What was surprising was that even with relatively few questions, right? So some kind of hundreds of thousands of queries, you could replicate the functionality of the model. That was the surprising part, right? So the setting is that so there's an adversary who is a potentially malicious client who has maybe bought legitimate access to your model by paying a subscription or whatever. And the goal of the adversary is to replicate the functionality of the model. And there could be two ways of doing this, right? So one would be that the adversary wants a model, wants a surrogate model, the stolen model, to be an exact copy of the victim model. And why it might want to do that is, remember that I told you about adversarial examples in the beginning. Adversarial examples fool a model into doing something wrong, right? And I also told you that sometimes adversarial examples are transferable, meaning that if you could fool a certain model for a certain task, the way you fool that model might also apply to some other independent model. So imagine that this is like the model that's used for access control using face recognition to this building. And the adversary's goal is to fool that model. And they can try to fool the model directly, but they might get caught because they might interact with the model multiple times, and somebody might get suspicious. But instead, if they could steal the model, then at leisure, they can try to figure out how to evade this model. And then if they are lucky, that would be transferable. That adversarial example would be transferable, so they can sort of go back and try this. So I steal the computer vision model that's here. And then I try to sort of put on makeup or put on glasses or whatever until I can fool my stolen model, and then the same makeup and the same setup might fool the original model. That might be one reason. And that's called fidelity stealing, because you want to steal the exact functionality. But quite often that is not what you might care. What you might care is the actual functionality, right? So if you want to steal a translation model, you are happy as long as it does a good job at translation. You don't need it to be the exact same model that Google has, right? So that's called functionality stealing, where you don't really care about the model having the same weights, but you want that your model, your stolen model, should have a good level of accuracy, hopefully comparable to the target model. So early work, I already alluded to this. Early work showed that simple models could be stolen. My students became involved in this about 5 years ago. They showed that neural networks could be stolen, and this has now continued. There's a lot of work showing that all kinds of models could be stolen. I'm not going to go through that because I want to sort of get to the more interesting parts, but the slides are already online. So in these slides, you would see examples of an image-to-image model being stolen. So there are these models that are called style transfer model, where you sort of give a photo and then say, turn this into the style of Monet painting or something like that. So one of my students showed that could be stolen easily. I already told you that there were people who stole Google Translate, like a certain variant of Google Translate. So there are examples of that here. But I'm going to go to this last bit, which is whenever we show examples of how classifiers could be stolen. So people always ask, like, well, how does that apply to generative models? And even before the DeepSeek story, you may have heard about this story where people at Stanford, this was when the first version of ChatGPT came along, perhaps it was ChatGPT 2, they showed that by using ChatGPT 2 up to about $600 worth, they could take an existing model. I think it was like a Llama model from Meta. They could take that as sort of a pre-trained model, and they could refine that using responses that OpenAI's model sent. And they now get a fine-tuned model, which they call Alpaca, just like llama. It's another South American mammal. And they showed that Alpaca could actually outperform the ChatGPT version 2 model, using which they were fine-tuning that. And it only cost them $600. right? So that was the sort of first public example of a model extraction using the API. And this was about 2 years ago. It so happened that Stanford had to pull that model down because nowadays a model is not just a model. There are also all kinds of safeguards in front, like a filter in front and a post filter and so on. Alpaca didn't have all that. So very quickly, Alpaca turned into outputting inappropriate content and so on. So they had to pull that out. When Google came up with Bard, I think there were also rumors that Bard may have been derived from ChatGPT's model. And I think Google sort of robustly defended that they didn't do that. But the fact that the question arose should tell you that model stealing is in the minds of companies in this business. And then we saw this early example of OpenAI accusing DeepSeek. So by now, I hope I have sort of convinced you that the model stealing is an important concern because it undermines the business advantage that the original model owners have. And what I didn't sort of maybe explicitly tell you is that none of the existing defenses are good enough for detecting or preventing model stealing. And then the question is, if you can't detect or prevent, what can you do about that? So let me sort of talk about this part a little bit more, like what can be done to counter model stealing. So the first thing you might think of it, if it's an undesirable thing, can we either detect it and then sort of stop it from happening, or at least stop it from impacting it? Or even if you can't detect it, can you engineer a system in such a way that the adversary is not going to benefit from stealing a model, right? So to prevent it, you could do things like, so for detecting it, you could do, what you essentially need to know is that you have a model and you have like thousands of clients who are using the model. You want to be able to distinguish the queries from a potential model stealer from everybody else. If you can do that, then you can detect and isolate the attacker, right? If you can do that if you make very strong assumptions about the adversary capabilities. So for example, people said that if the adversary doesn't have enough natural data, that they have to use synthetic data, then you can use the difference between the distribution of synthetic data and the distribution of natural data to say anybody who is sending me synthetic data is potentially somebody who's trying to steal a model. So to put it in other words, assume that I have a X-ray diagnosis model. My model expects X-ray images, and it's going to output diagnosis. And let's say that X-ray images are hard to come by. So if you are a model stealer, if you're a doctor, you're going to use an X-ray image, and you might, I might let it through. But if you're an adversary who's trying to steal a model and you don't have enough X-ray images, you're going to use random images, or you're going to use artificial images. And if I can now tell the difference, I can say these images are not coming from a doctor because they are not X-ray images, and therefore I can throttle you down. I think that's a very strong assumption. I think there is hardly a situation where the adversary won't have enough natural images. X-rays are plentiful. You can download X-rays from the internet. You might be in very niche setting where the inputs for your model are so specific that an adversary won't have access to it. In that case, you can tell the difference between queries that are coming from a legitimate client and queries that are coming from a potential model stealer. But it doesn't apply to most cases. But even if you can't detect it, you might be able to somehow prevent it. And a good way to prevent it is to add a cost, right? So take the X-ray example again, right? So even though model stealing can be done with reasonable, surprisingly small number of queries, they are still quite high. Right, so these examples that I showed you require something like 100,000 queries to be able to steal a model. So a legitimate doctor is probably going to ask, 10 diagnoses a day, right? So if you can associate the cost with each such diagnosis request, if you can say, when you send an X-ray and want a diagnosis, it's going to cost you 1,000 rupees. It's not going to impact the functionality of a doctor because they're only going to ask 10 queries a day. But it will affect the ability of an attacker to steal your model by asking 100,000 questions because it's going to cost them 100,000 times $1,000, which may not be cost effective for them. Right? So in this case, adding a cost to each query will effectively thwart an attacker without inconveniencing legitimate users. But as you can see, it might not work in all cases. Think about autonomous driving. In autonomous driving, the model has to classify 25 frames a second, right? So they are going to, a legitimate client is going to send you 25 queries every second. If you now add a cost to that, it's either too high so that it will thwart the usefulness to legitimate users, or it's too low that it's not going to prevent an attacker from asking a next query and stealing a model. So the consensus now is that neither prevention nor detection is feasible in the general case. It may be feasible in specific niche application. If you're lucky, your application is such a niche application that you might get away with either a prevention technique where you try to distinguish between queries that come from an attacker versus queries come from legitimate customers, or a technique where you add a cost and you don't really know who is an adversary, but because of the cost, the adversary is it no longer is cost effective for the adversary to steal the model, right? So neither of them is feasible in general. Then what can we do about that? So this is where I sort of wanted to go back to the thing where I put this steal in quotes, that essentially model stealing is model derivation, right? You start from a model, and then by querying that model, you build another model. That may become the sort of dominant business model for people who build models and make it available to others. And in fact, we see evidence of this already. Like, so nobody these days trains models from scratch. They start from some foundation model, and then they use their data to fine-tune that model. And these big model providers even provide that as a service. So if you go to OpenAI, they have a page about model distillation. They provide an API that allows customers to use OpenAI's model as a way to sort of distill the knowledge of embedded in that model to build their own specialized models. But that doesn't mean that they are happily allowing anybody to distill models from their own models. And we saw that from this DeepSeek saga, right? So even though OpenAI is actively encouraging people to distill from their model, they were unhappy that when they thought that DeepSeek did the same thing, right? So essentially, model distillation would be sort of a desirable business model, assuming that the model owner gave permission to do so, right? So some kind of license agreement for people to distill their models. So what it seems like you would need is, you don't necessarily need to prevent or detect model stealing or model distillation, but if it happens in an unauthorized way, there needs to be a way to demonstrate that a derived model or a suspect model is in fact derived from the original model. So this is what we call the model ownership resolution scheme, right? So in the literature, there have been two different types of approaches to resolve model ownership. One is called watermarking. The other one is called fingerprinting. So watermarking, as you can imagine, is taking something and then adding something to this original artifact or object in such a way that if it was used in an unauthorized way, you can point to that artifact and say, that was stolen or that was derived from mine, right? So you've probably seen this in images. Sometimes images are watermarked, right? There may be sort of a little sign on the bottom of the image saying who owns it. It may be also hidden, right? So when I started giving these talks, I heard examples from people that dictionary makers apparently used to watermark their dictionary by having a nonsense word somewhere, right? So if I publish my dictionary and I have a nonsense word with a nonsense definition, and he steals my dictionary blindly, I can tell him that that's my dictionary because it has a nonsense word. Map makers apparently used to do this. They have a map, and then they put some kind of a non-existent place, and somebody who steals the model, because they didn't know that the model was watermarked in this way, would sort of carry over the watermark. That's the idea in model watermarking as well. Fingerprinting is you don't add anything, but you extract something inherent and use it as a way to sort of identify a model. So it's like our fingerprint, right? Our face is a kind of a biometric, fingerprints are biometric. You can think of this as a biometric for models. So people have proposed both of these. So watermarking, the general idea would be, you have a, so typically when you want to train a model, you have data that lies in some manifold, right? So you have a k-dimensional space, but your data is not uniformly distributed in this space. It lies in some particular shape. and they pick some data that's outside this manifold, right, and then mislabel them intentionally and train a model with the actual data plus this watermark data. And the reason they take it away from the manifold is that then it will not influence the model because it's sort of far away from the normal data. And then the hope is that because it's far away, the model is going to memorize that. So if you now steal my model and I ask you a suspect model questions using this watermark data, then it's going to respond in a way that I can predict, right? Like just like map makers did and just like dictionary makers did. That's the idea of watermarking. But the whole idea of watermarking is that I do this while I'm training a model, right? When I'm training a model, add a watermark and train the model. That works to deter white box theft, right? If you try to steal the model bit by bit, then you would inherit this watermark. But model extraction is not the case where you steal the model bit by bit. Model extraction is you asking queries from my model, and then you are training the model. So you're not going to oblige by adding some watermark that is chosen in a way that will not affect the original functionality of the model. So that's a problem. It cannot extract model extraction. It cannot resist model extraction. If you want to resist model extraction, the only option you have is it's the adversary who is going to ask you queries. And if you want to watermark, meaning that if you want to sort of misclassify, in the case of a classifier, if you want to misclassify some of the answers, you have to take a subset of these questions that a client is asking and then intentionally give back wrong answers, right? So you don't want to do this too much because that would then destroy utility for legitimate users as well, right? You don't know who is a legitimate user and who is a model thief, right? So you can do it in a small minority of cases, and my students showed that that can be still effective, right? So you can embed a watermark by intentionally wrongly answering some of the questions chosen by the adversary, and if you do it in such a way that later on you will be able to use that to demonstrate that a model has been stolen. Neither of these is really satisfactory. So there are two problems with watermarking. One is that because you are adding something, right, that no matter how careful you are, it is going to affect the utility of the model, right? Because you're giving wrong answers. You're training a model with wrong answers, right? Which compared to training a model with clean data, adding some wrong answers, no matter how small, is going to impact a model. So there's always this trade-off. But more importantly, many people, including my colleagues at Waterloo, have shown that all of the existing watermarking schemes are brittle, in the sense that an adversary who knows what your watermarking scheme is can remove the watermark or degrade the watermark sufficiently so that the watermark detection fails without destroying utility while still retaining utility to a suitable extent. And this is also how watermarking in other domains have been broken. So image watermarks are broken if somebody can remove the watermark sufficiently while the image still looks good enough. So the second aspect is fingerprinting. Fingerprinting is you don't add anything. So there is no problem with utility because utility doesn't change. You don't change the way the model is trained. But you try to extract something inherent to the model. So there are a number of fingerprinting schemes. The problem with them is that they're all expensive. So even the best fingerprinting scheme requires training hundreds of models and then try to find something that is characteristic or inherent to the model. So imagine going to a company and say, like, if you want to protect your model, you can use a fingerprinting scheme, but instead of training one model, now you have to train 100 models. They are not going to buy that, right? So because it's like 100 times the number of computers and the number of GPUs you should have. So the state of the art is that, so first of all, detection and prevention is not feasible in general and might not even be desirable because this model distillation might actually be a good business proposal or good business model. That leaves us with ownership resolution. There are two kinds of techniques, fingerprinting and watermarking, but they both have their own share of problems, right? So watermarking is brittle and harms utility. Fingerprinting is not brittle and will not harm utility, but it can be expensive. So I think I have about 10 minutes. So I think rather than talk about these model ownerships, whether these ownership schemes are robust, and the short answer is that they are not robust. And we give an example of a specific way in which all model ownership schemes fail. I want to skip to this thing because I think as practitioner, this is something that that you might appreciate. So let me go there. So far I talked about model stealing and how to do model stealing, how to prevent that, right? And this is very typical of academic research, right? So I have a student who needs to write a thesis, and they focus on model stealing. And then somebody else has a student who focuses on differential privacy. Somebody else has a student who focuses on poisoning and poisoning prevention. And this is natural, right? Because you sort of limit the scope of what you have to do so that you can do a good job. But if you're a practitioner and you have a model to protect, you probably want to protect against multiple events. You don't want your model to be stolen. You don't want your training data to be leaked. So you want to apply differential privacy. You don't want people who provide data to you to poison the data. So whenever we go and ask people, companies, why don't you deploy our fingerprinting scheme or watermarking scheme, the question they ask is like, you asking me to deploy this, somebody else is asking me to deploy the other thing. How would they interact? And it turns out that there is surprisingly little work done in this about this combination.